So I'm going to do a quick review of what we did right before we went on break. So what we did, we started with waves. So I'm just going to really quickly just review. This is stuff that you already have in notes. So we have wavelength, lambda, which is just the length of the wave. Um, we have frequency, lowercase f, which is the number of waves that pass a point in a second. That's going to be measured in per second, 1/second, or hertz. All of these are the same. By the way, this is also just measured in meters. The other thing that we need to know is the period. This is big T. This is the time for a wave to complete one cycle. This is measured in seconds. We also have the speed of a wave. Which is going to be v. This is how fast the wave travels. This is going to be meters per second. And then amplitude. This is big A. And this is the height of the crest from equilibrium. So a wave would look kind of like this here. Here's our parts of the wave. That line marks the equilibrium. From the equilibrium to this point here, which is the crest. That's your amplitude. From crest to crest, that's your wavelength. So the basic equations that we came up with was the speed is equal to your wavelength divided by your period, or the speed is equal to the wavelength times the frequency. We can also just look at the relationship between frequency and period. They're reciprocals of each other. The frequency would be 1 over the period, and the period would equal 1 over the frequency. Okay, so let's look at how something looked different if we change the speed but keep the same frequency. This was in the concept builder that we did, and it gave a lot of us trouble. It was kind of difficult to look at, so I'm going to try to do a little bit better explanation. So, for example, if we look at a wave, and so we have a wave here. Let's say from here to here is 1 meter. And that took 1 second to complete. That the time for that, it took 1 second. So the speed would be 1 meter, 1 meter per 1 second, which would be 1 meter per second. Frequency, there it is, one wave, because it goes from one point to that same point, so this is one wave. In 1 second, giving us a frequency of 1 hertz. So let's say we then double the speed. So the speed now is 2 meters per second for the speed. But we want the frequency to stay 1 hertz. So I need one wave, one complete wave in a second, but it needs to be 2 meters long to be to have the same speed as, or to be double speed. Or it, yeah, so 2 meters long in that 1 second. And I need one wave in a second. So just going off these hash marks here, that's 1 meter. That'd be about 2 meters. So this was 0 meters, 0 seconds. This would be 1 meter, 1 second. This is 0 meters, 0 seconds. That's where the wave would start. It needs to complete a wave after 2 meters. And that's only going to take 1 second for it to complete. So what would it look like? It would have to go like that. So here, if we're looking at that same section, that 1 meter, this only happens in half a second there. So it looks like the wave has been stretched out. It's really just moving faster. That's what's happening here. So it's just moving faster. So it looks like the frequency has decreased because there's only half this wave, but you have to see that that's only half the time. If you look at the full 1 second, they have the same frequency. Okay, just twice the speed.